Bismillah ar-Rahman ar-Rahim. Alhamdulillahi Rabbil Alameen. Wa sallallahu wa sallam ala Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. This is our second of three concluding lessons in our course on Islamic logic. And in this lesson, we'll consider the answer to the question, has modern logic replaced ancient logic? As we saw in the previous lesson, in which we investigated the answer to the question, has modern science replaced ancient logic? The use of the terms modern and ancient is a use of the technique of poetics, one of the five arts of falsafa. And the word modern has an attractive power to the listener that attracts him or her to modern logic because it's modern. And the word ancient has an opposite effect on the listener, and it repels him or her from ancient logic because it's ancient. And we saw in the previous lesson that the reason for this attraction and repulsion is our attachment to the life of this world. Allah subhanahu wa ta'ala says, بَلْ تُؤْثِرُونَ الْحَيَاةَ الدُّنْيَا وَالْآخِرَةُ خَيْرٌ وَأَبْقَى. But instead you prefer the life of this world, even though the afterlife is better and more enduring. So in order to answer this question objectively, we need to, first of all, remind ourselves of this verse and emphasize within ourselves the tremendous value of Islamic logic, because it was through Islamic logic that all of the sciences of the Muslim scholarly tradition, they flourished, and that's how our religion was preserved, and that is tremendously valuable. We have to remind ourselves of that. And then let's try and rephrase the question in a more neutral way and replace modern logic with the logic that is used by the contemporary academic community. So if you go to a university, the logic that you will study is not the logic that you've studied in this course. You will study something that looks a little bit different, or a lot different, as you'll see soon. And let's replace ancient logic with the logic that was used by the Muslim scholarly tradition. So with that, let's move forward. And let's take an example of an inference that is used in the Muslim scholarly tradition. So here's an important argument that we will study in great detail in our follow-up course on Islamic theology. And the argument goes as follows. This is a syllogism. This is a categorical syllogism which we've studied in this course on Islamic logic. And it goes as follows. Everything in the universe is contingent, and everything that is contingent depends on a necessary being. Something that is contingent is something that could have been otherwise. So the sky could have been a different color than it is. The rain could have fallen in a different way that it does. The wind could have blown in a different way that it does. Everything in the universe could have been some other way. And that leads us to ask the question, why are they the way that they are? What made them the way that they are? And the argument proceeds that every contingent thing, everything that is contingent, must depend ultimately on the action of a necessary being. Someone who is not contingent, someone who is not made to be who he is by anything else, and that's Allah subhanahu wa ta'ala. The details of this argument we will defer to a subsequent course. For now, let's look at this argument and see how Islamic logic is employed in the construction of this argument and the derivation of the conclusion. So this is a categorical syllogism of the first figure. The first premise is on the pattern all A is B. The second one is on the pattern all A is C. And we've seen it's a simple categorical syllogism of the first figure, the first mode of the first figure. And the conclusion is all A is C, which in this case is simply everything in the universe depends on a necessary being. So here's a simple application of the logic that we've learned, the logic that's used in the Muslim scholarly tradition, Islamic logic. The question now is this reasoning different in contemporary logic? Well, let's see. So in contemporary logic, we would take the first premise, everything in the universe is contingent, and we would represent it like this. Now, this doesn't seem very readable and understandable, and in fact, contemporary logic if you want to learn it, you have to go through a process of technical training. You need to have a background in mathematics, and also computer science background helps. So contemporary logic is taught mainly for mathematicians and for computer scientists. We'll see that more on that in a little while, inshallah. So what this means is, this says for all x, ux, this is these are called propositional functions. Ux and cx means over here these represent statements. They represent propositions. So ux represents the proposition that that x is something that is in the universe. So x is a thing that's in the universe, and cx is saying that it's contingent. So ux is x is a thing that's in the universe, and cx says that that thing is contingent. The x is called a logical variable. It applies to in this case, it applies to all of the things that are in the universe. In other cases, it can be limited to apply to other things. It can be limited in scope. There's something called the universe of discourse that is defined when you employ contemporary logic. So x is called a logical variable, and these two symbols, the upside down A and the arrow sign, these are called logical constants. They're called logical constants because they have a constant meaning in every logical representation. So the upside down A always means for all, and the arrow is an implication. So what this is saying, that for every x, if x is something in the universe, then x is contingent. So this is how, using contemporary logic, one would express the statement that everything in the universe is contingent. One would say, for all x, u of x implies c of x, where u of x is a function that is defined as x is in the universe, and c of x is a function that is defined as x is contingent. So if it's true that x is in the universe, then it's true that x is contingent. So that's our first premise. Let's take the second premise. Everything that is contingent depends on a necessary being. We follow the same process, just change the function. So c of x is the same. This is saying for all x, if x is a contingent thing, then D and B depends on a necessary being for its existence. And so these two formulas, logical formulas, they are our two premises. So the one on the left is the first premise, the one on the right is the second premise. If the way that in contemporary logic, the way that you join the two premises, what we're saying is that if both premises are true, then the conclusion is true. So we put brackets around each premise, and we put another logical constant, which is the and sign. And so this means that so the statement saying that the two premises are true is to say that for all x, u of x implies c of x, and for all x, c of x implies d and b x. So this is a statement of the two premises. It's saying that it's true. Now, the way that you proceed in contemporary logic is you now want to simplify this complicated looking formula using something called rules of inference. Rules of inference, this is an important term that I'm going to come back to later in this lesson. And the rule of inference that we're going to use is called hypothetical syllogism. Wow, that sounds like just what we were doing in Islamic logic. So it says there's a rule of inference which says, it's called the hypothetical syllogism. It says that if you have a proposition P, if it's true that P implies Q, and it's true that Q implies R, then P implies R. You get rid of the Q in between. So in this case, our P is X is in the universe, our Q is that X is contingent, and our R is that X depends on a necessary being. So you can simplify this to P implies R, where P is U of X, and R depends on a necessary being. So using this rule of inference, which can be proven in this logical system. Logical system is an important word that I'll come back to in a couple of slides, inshallah. We come to the conclusion that for all x, if x is in the universe, then x depends on a necessary being, which looks exactly like our conclusion above. Therefore, everything in the universe depends on a necessary being. So, so this is our statement of the two premises, and these two premises, this complicated looking symbols, collection of symbols, is basically saying the first two premises above that are stated in simple English. Everything in the universe is contingent. Everything that is contingent depends on a necessary being. And we simplified it using something called rules of inference to the conclusion, which is stating the same thing that our conclusion above stated. Therefore, everything in the universe depends on a necessary being. So let's return to our question. Is this reasoning different in contemporary logic? This reasoning that everything in the universe is contingent, everything that is contingent depends on a necessary being, therefore everything in the universe depends on a necessary being. Did modern or contemporary logic reason any differently? It didn't. It simply stated each premise in a different language, and it stated the conclusion in a different language, and you had this thing called a rule of inference, and you reached the conclusion. In fact, it seemed a little bit more complicated because what we learned in Islamic logic is intuitive. It's a natural language. Everybody understands it. Anybody can learn it. You don't need to be a mathematician to learn it and use it. But whereas over here, you need to know algebra. You need to be a mathematician. If you haven't studied some basic math, then you won't do very well in contemporary logic. So contemporary logic, in this case, the fact that we used all of these logical variables and logical formulas and logical constants and rules of inference, big sounding words, it didn't really seem to add anything. We state the premises were the same and the conclusion was the same. So why would somebody want to reason with contemporary logic? The brief answer is that contemporary logic allows you to reason about reasoning. Let me try and explain as simply as possible what that means. So what you can do is you can take the logical variables that we saw in the formal language of contemporary logic. These are, remember, the x's that represent instances in the real world, or we'll see they could also express instances in imaginary worlds or no worlds at all. You can also take the logical constants, which are like the quantifiers and the arrows of implication. You can take propositional functions, and you can take the rules of inference, such as the hypothetical syllogism rule of inference, and with all of these ingredients, you form what logicians call a logical system. You can then take a logical system and you can formalize it. You formalize it by first making what they call an axiomatization. Axiomatization is, it represents the statements of the formal language that are defined or declared to be true. So let's take an example. The first statement here, it uses Greek letters. It says that alpha implies, the truth of alpha implies that implies the truth of the proposition or the collection of propositions. Beta implies alpha. So what this is saying is that if alpha is true, then beta implies alpha is true. This is a tautology. It's obviously true. But over here, the point is not that it's obviously true. The point is that it's defined to be true. It's defined to be true as an axiom. Axioms are not proven. They are defined or declared to be true, and they are taken as givens. The second axiom is similar. It states that the compound proposition that the truth of alpha implies that the truth of beta implies gamma all in brackets as you see. The truth of this, if this is true, then this implies that the truth of alpha implies the truth of beta. The truth of this statement as a whole implies that the truth of alpha implies the truth of gamma. And this is another axiom. And you have a third axiom below that you can kind of work your way through if you like. The thing to note here is that the Greek letters, they are not, these Greek letters, these are symbols of what logicians call a meta-language. They actually represent propositions. So alpha represents any proposition alpha in the propositional logic set, or the propositional logic that's used in the propositional logic calculus. It is represented by alpha, and any proposition is represented by beta. So these are statements about statements of logic in the formal language that we have seen so far. And so we step back and we axiomatize and we say that any statement that is like this is going to be defined as true. These are axioms. Then what you do is you define a rule of inference. A rule of inference allows you to move, we saw as in the simple illustrative example, it allows you to move from the truth of one statement in the formal language to the truth of another statement in the formal language. Logicians say that rules of inference, they preserve truth, and they transform statements and they preserve truth. And so this rule of inference, it states that if it's the case that alpha implies beta is true, and if it's the case that alpha is true, then the conclusion is written by convention underneath the line. The conclusion is that beta is true. There's modus ponens, we've seen this before. So, in fact, with those that three axioms and with this rule of inference, this is one formalization of a kind of logic, a kind of logical system that contemporary logicians, they refer to as propositional logic. And with these, you can, with these simple axioms and rules of inference, you can just take any statement in the formal language and just apply you can take any statement in a formal language and apply the axioms and rules of inference to transform it into some other statement, and the end result will always be true by definition. It's been a while since I've done this, so if there's any expert logician who's listening who noticed any inaccuracies in what I said, please let me know. I'll be happy to refine the statements. But at a high level, this is what's happening. And through axioms and rules of inference, you formalize a logical system. So what we're doing here, what contemporary logicians do, is they take premises in natural language. Natural language is the way that we speak. So a natural language premise that we just saw was that everything in the universe is contingent. This is a natural language premise. They then translate this natural language premise into a different language, a formal language, such as the language that we just saw. And this language has rules, has a grammar that's formally defined. And then they calculate using the natural language premises that have been formalized, such as the two premises that we just saw in our illustrative example, and they apply the rules of inference to see if where it moves you, where it takes you to, what statement's truth it takes you to, and then they take the final statement in the formal language that was the result of a series of rules of inference, a series of calculations, a series of operations, and you translate that back into the natural language conclusion. And this is a precise way of showing that a set of natural language premises lead to a natural language conclusion. What logicians do now, contemporary logicians, they focus on the formalization and the calculations. This is the area of contemporary logic. Contemporary logic is different than Islamic logic. I'm going to show you at the end of this lesson. It's a different exercise. It has different goals. It's trying to do a different thing. Even though you can use contemporary logic formal languages to reason, to describe the same kind of reasoning that we do in Islamic logic, there are some very important differences because it's trying to do something else. So a logician, he studies the formal languages, the axiomatizations, the rules of inference, and he'll ask questions about these formal languages and rules of inference and axioms and logical statements, logical symbols, logical constants, and variables and propositional functions. He'll ask questions like, can every truth be proven? Let's say that there is a statement in the language, in the formal language that we've defined and whose axioms we've defined and whose rules of inference we've defined. Can every truth in this language be proven or not? If it can be proven, then they say that this language, this formal language, is complete. If not, then it's incomplete. So you have this notion of completeness, which is an important idea that's studied by logicians. Now, what you can do is, if you just look at the area that logicians study, they study the formal language and the calculation, the movement from one formal language statement to another formal language statement in a way that preserves truth. The formal language is essentially a collection of abstract objects. They happen to be propositions, but what they actually are, whether they are propositions or whether they are airplanes or whether they are numbers or whether they are something else, it doesn't matter because the formal logic, the meaning is completely abstracted. What it is, it doesn't matter. It's just some abstract object and then a collection of axioms and operations. And if you've done a little bit of math or algebraic theory, for example, you will immediately recognize that this is exactly what a mathematician studies. Math now is not what it used to be. Mathematics in pre-modern times, it was subjects like geometry and arithmetic. And geometry and arithmetic, they actually represent things directly in the real world. So when you study angles, you study shapes, and these angles and shapes, they exist in the world. You study natural numbers. Natural numbers. Some of you might have heard of natural numbers. Natural numbers, they begin at 1, 2, 3, 4, 5. Why 0 is not a natural number? 0 is an integer, but it's not a natural number. Why are 1, 2, 3, 4, 5 called natural numbers? Because you use them to count real things. You count how many, there's 1 cup, and then there's 2 cups, and then there's 3 cups, and then there's 4 cups, and so on. And so these are called natural numbers. And with natural numbers, you do things like arithmetic. So in pre-modern times, math was thought of as geometry and arithmetic. But now you have math includes things like imaginary numbers. What's an imaginary number? An imaginary number is an imaginary number. It actually doesn't represent anything directly in the real world. And it includes a number of other, it's the study of numbers that you can't even express. Study of numbers that are irrational. They cannot be expressed in a ratio. and if the number of decimal points never ends. So what do these numbers represent in the real world? What are these numbers? Can you even write them down? Math is, and now you have the important part of modern math is this idea of sets and set theory, and it would take a long time to explain the details of that, which are, it's not my specialty, but I only have a understanding. Only have an understanding of it as a distance, but even then it will take a while to explain. So I'll leave it for you to read up on that if you're interested, if you're not already familiar with it. But all of these things in math, they are basically, they can be thought of as abstract things that may or may not represent something in the real world. It doesn't matter whether they represent something in the real world. This is important. We're going to come to it because we're going to see that it doesn't matter in a logical system, and you can have many logical systems, whether or not it represents things in the real world. That doesn't matter. That's not the concern of logicians. Logicians are concerned with the study of formal logical systems, and they ask questions about them, and you can change the logical system, and you can ask other questions about them. And that's why you have this complicated language and complicated way of representing logical reasoning, because if you represent logical reasoning in this way, you can ask these questions. But if you don't represent logical reasoning in this way, it is very difficult to ask these questions and work out the answers to these questions. And so this is so abstract objects and a collection of axioms and operations and defining them. This is actually a study of abstract mathematics, and mathematics is very important because this is the language of science, and so in mathematicians they've found that they've taken some abstract objects, they invent something like an imaginary number, they do all of these things with it, they say, wow, this is really cool, if you kind of define this that doesn't exist anywhere in the world, and you define these operations, this really interesting thing happens, and if this happened, it proves that this is true and this is true, and wow, this is so beautiful. And then they do all of these things, and then the scientist finds that these, using this mathematical system, you can actually model the working of the real world. You can put in certain values to a number, and you put it into this yellow box that you see here. You translate it into an abstract object. You have a collection of axioms and operations, and you do various things on it, and you reach and a result comes out, and that result actually, and the input and the output, they represent the way that the universe works. That you do something, and then the result of that is going to be this. And if something is the case in the world, then the result of it is going to be this. It's very subhanAllah, it's amazing, and there's people who have written books on this. And why is it that the universe actually works in this way, and you can develop, and human beings have the unique ability to develop these kinds of highly abstract mathematical systems, and then the universe ends up working. These mathematical systems, they end up describing in some way the way that the universe works. And so, and it's because Allah subhanahu wa ta'ala has made it that way, and it's a sign of His wisdom and design. It's a sign of His existence. But over here, what's interesting is that using this formal language that we just saw, it's actually the same thing in math, and the same kinds of questions that you ask about a logical system, you can ask about a mathematical system. You can ask about a mathematical system whether or not it's complete, for example. Then what you can do is you can take this collection of abstract objects and axioms and operations and kind of put them together and think of them as a collection of bits, a collection of zeros and ones, and a collection of logic gates. The logic gates are like AND gates and OR gates and NOR gates, and if you've done so in computer science or computer hardware, you'll study this, and you can, and it's actually the same thing. You can, there's something coming in, and a collection of zeros and ones coming in, and that's you can think of as the natural language being translated and brought in, and there's a collection of zeros and ones that go out. A logical system that's viewed in this manner is studied by computer scientists. A computer scientist would study this logical system and ask the question about whether a computer scientist would focus more on the operations between logical statements, the transformations, the inference methods, the inference steps, the rules of inference, and the computer scientist would study the whether in order to solve a particular problem, you can write an algorithm, a series of steps on that describe the operation of a computer, and an algorithm that terminates. So a computer scientist would look at a logical system, but in this case it represents a computer, and he would ask whether the series of steps that are described in order to transform the zeros and ones into different zeros and ones, does it terminate or does it go on forever? This is important to computer scientists because they want to know whether particular real-world applications of computing can actually be made, whether computers can really solve certain problems. And there are certain problems that are called decidable problems, and decidable problems are those in which the computing that can be computed because an algorithm will terminate in a finite number of steps. There is another category of algorithms that are undecidable, and they will never terminate in a finite number of steps. And then there's things in the middle, and there's ways that you can write heuristics in order to solve undecidable problems. And these are all of these questions. They are asked and they're studied using the same formalization techniques of logic, which are the same as the formalization techniques of mathematics. And we've seen they're now the same, very similar to the formalization techniques of computer scientists. So that's why this system, so the questions that we just asked, questions like questions of completeness, decidability, and there's other questions that can also be asked. These are questions that are asked of logical systems, they're asked of mathematical systems, they're asked of systems in computer science. And in fact, that's why the contemporary logic finds its greatest and most useful application in mathematics and computer science. So if somebody is a computer scientist or a mathematician, they will have to study contemporary logic because that's where it's mainly applied. So if you step back for a second, keep that thought in your mind. Think for a moment about the axiomatization. I talked about this earlier as well. Axiomatization, it is defined as true. And the operations on those axioms that preserve truth are defined as truth preserving. What that means is that you can actually define any axiom that you want as true and any rule of inference that you want as truth preserving, and you can make up a system and then you can study it. So you can define a logical system that tolerates P, proposition P is true, and its contradiction is true. You can define it. You can define this as a true statement, the law of non-contradiction. The law of non-contradiction goes out the window because you have defined that that a proposition and its contradiction, not that proposition, are true. And in fact, people do that, and this area is called paraconsistent logics. You can define paraconsistent logical systems. These are logical systems that tolerate logical contradictions. Now, this might seem absurd at first when you first hear about it, but in fact, it's quite useful because there are many real-world problems where you might come to a conclusion that appears that creates a logical contradiction, but in fact you were mistaken. And if you keep on computing, you will see that it turns out not to be a logical contradiction, and you will come to a solution to the problem that you're trying to solve. That's how we work, actually, and we consider various options, and some things are contradictory. We test it, we keep it for a while, we modify something else. And so the value of a paraconsistent logical system is that you can use it to solve problems in this way, where the truth might not immediately appear, and you might have to work with logical contradictions for a while until they disappear. So it's a useful logical system for computer scientists, for example. Also, you can define a system in which not only can a statement be true, false, but it can also be something else, neither true nor false. It can have many truth values. And these are called multi-valued logics. And a relative of multi-valued logic is something called fuzzy logic. These are logical systems that are, again, useful, especially to computer scientists, because you can solve problems potentially more powerfully. Because if you're limited to translating the real world into zeros and ones, then you will need a lot of zeros and ones and a lot of manipulations of those zeros and ones. But if you can translate it into more than two values, then, and you develop a way to work with those more than two values and operations, then you can conceivably solve complex problems in fewer steps. So fuzzy logics and multi-valued logics, fuzzy logics have other computing applications too. They're very useful. They're useful systems, and a logician or a computer scientist or a mathematician can study those systems and tell you about whether it's complete or whether it's decidable or whether it's this or whether it's that, and you can do useful things with it. Now, the question that this raises is, do these definitions represent reality? So when you define that a proposition is true and its contradiction, a proposition and its contradiction are both true, and you've done something with it, you can solve problems with it, does it represent reality? What is truth, by the way, anyway? And what does it mean for one statement to entail another statement, really, in reality? Not the way that you define it, but in reality, what does it mean? These, in fact, are not questions of contemporary logic. A contemporary logician is not concerned with those questions, or maybe he is, and he'll have some opinions about it, but they're not in his realm of expertise. Nor are they questions of contemporary math, nor are they questions of contemporary computer science. Contemporary logic, math, and computer science are concerned with studying the properties of logical systems. They're not concerned with questions about reality. These questions are, in the contemporary academic world, they're questions of contemporary philosophy. They're not questions of contemporary logic. And that's important because they are questions of Islamic logic. And we briefly treated some of these questions during this course. And so what you can think of it like this. Islamic logic this is a field of study called Islamic logic. And with Islamic logic, you can use Islamic logic to correctly discover the truth of the truth regarding answers to questions about who created me. You can prove that I was created by God, by Allah subhanahu wa ta'ala, and Islamic logic will is a series of rules that teach you how to come to that conclusion and see that it's really true in the real world. It's not something that you want to compute, but it's really true in the real world. It will help you demonstrate that the Prophet Muhammad sallallahu alaihi wasallam is the messenger of Allah. It will help you demonstrate that the Quran is the word of Allah subhanahu wa ta'ala, that you are commanded to pray, to fast, to give charity, and that after you die, you will be resurrected. So Islamic logic is a collection of techniques which if you follow, techniques and principles which if you follow, you will arrive at correct answers to real world questions such as these. Now, there is a section of Islamic logic that you can cut out and represent in contemporary formal logic. The notations, the symbols that I just described. There's another section of Islamic logic that you can cut out and take in and discuss in contemporary philosophy. So there are questions of in Islamic logic. One studies questions related to epistemology, how you know that something is true. You study questions related to metaphysics. What is it that exists? What's the relation between the thought in the mind and between experimental reality? We briefly touched upon some of these questions during this course, and that's important because you need to know these things before you can accurately discover the answer to the questions that you see on the slide here. So what happened was that in the modern time, that the Islamic logic is barely anybody studies it or understands it or teaches it in a thorough way, that I just described. And you have questions of it that are found in contemporary philosophy, questions of it that are found in contemporary formal logic, and then contemporary formal logic and contemporary philosophy expanded in scope, and they discussed many other questions. And not only did they discuss many other questions, but they arrived at conclusions that actually make it very difficult to discern the truth of the questions that Islamic logic seeks to discover the truth of. In fact, it makes it very difficult to discover the answer to most questions because most 99% of philosophers who go through a philosophical education, logicians who do the same, the conclusion that they come to is that you cannot know anything. They're actually very confused. So if we just look at contemporary formal logic, because this was our point of departure for this lesson. Our point of departure for this lesson was has contemporary logic, or the methods of contemporary logicians, has this replaced Islamic logic? What we can say is that contemporary formal logic is very useful for making computers and can make computers better than Islamic logic can, because Islamic logic wasn't designed to make computers. We can say that it's very good for making tall buildings, it's very good for making airplanes, and it's very good for making the material things that form our modern life. However, it's not very good for answering the questions that Islamic logic seeks to answer. Because there's a whole area that it ignores. And so if we return to our question, has the logic that is used by the contemporary academic community replaced the logic that was used by the Muslim scholarly tradition? The answer is no, it hasn't, because they're actually different things and they have different purposes. Contemporary logic focuses on procedures that lead to short-term material prosperity, and Islamic logic focuses on real-world truth inferences that lead to religious compliance. Contemporary logic, let's take that again, focuses on procedures. Contemporary logicians, the reason why they express things in such, and it looks as though it's obscure at first glance, If you don't know the terms and the techniques, the reason why they're so obscure is because they're set up in a way that you can study the way the reasoning works. So contemporary logic reasons about systems of reasoning, and systems of reasoning in quotation marks, because this now you need to expand to include mathematics and computer science. And the value of this is that it helps you make the material things of this life. Both are intricately, so mathematics is the language of modern science, and computer science is what helps us make computers, which help us make all of the things that we enjoy in modern life. And so contemporary logic focuses on the procedures that lead to short-term material prosperity. That's why in universities it's studied, it's most important for mathematicians and computer scientists. I have a computer science background, and that's where I studied contemporary logic. And I've worked with proofs and proving algorithms and NP completeness and all of these things. It's been a while, but that's where I personally learned it. Islamic logic, on the other hand, focuses on real-world truth inferences, and because it focuses on real-world truth inferences, it includes within it discussions that have been taken out of formal logic and placed in philosophy. So there are questions. So, for example, the implication, the if-then, the arrow sign in contemporary logic has a very different meaning than the arrow sign would in Islamic logic. In Islamic logic, it refers to a conditional syllogism. A conditional syllogism, if you remember, when we were studying it, we saw that the entailment, the relation between the two propositions of a conditional syllogism could be a real relation, could be a real implication, or it could be a coincidental implication. And what Muslim logicians are concerned with, they are concerned with real implications. In other words, when we look at the world, we can see that certain things actually entail other things because of what they are. But contemporary logic, it focuses on coincidental implications. That's why contemporary logicians, they use truth tables to define the implication. And you can read up on the topic of material implication to see the difference between these two things. They're doing different things. Islamic logic focuses on real-world truth inferences. It doesn't study how that reasoning, it doesn't seek to formalize that reasoning so that you can reason about reasoning, but it just directly studies real-world truth inferences. And these truth inferences, they are those ones, those truth inferences that lead to religious compliance. They're focused on the next world, whereas contemporary logic, the techniques of contemporary logic are focused on this world. So at the end of this overview, I'd like to apologize because this is a very complex topic, and I've presented things at a high level. These are basically a series of high-level remarks, but they are accurate, they are true. They do describe the relation of contemporary logic to Islamic logic. They do accurately describe what contemporary logic is. However, the problem is that if you're a non-specialist, there were probably many things that you didn't completely understand, and that's because of my inability to explain those things in a simpler language than what I just did. And if you're a specialist, if you're a PhD in computer science or mathematics, then you probably noticed, probably have a list of inaccuracies in what I said. And if you noticed anything, please do tell me. I'm interested in improving the accuracy of what I said. But nonetheless, at a high level, what I describe, it is true. This is how it is. This is the relationship between contemporary logic and modern and Islamic logic. And it's important to understand because people now, they often come with, they say that, well, now logicians have discovered fuzzy logic, And fuzzy logic, according to fuzzy logic, things can be true, false, or neither. And there's relativity, and there's no absolute truth or falsehood anymore because of what contemporary logicians have discovered. And this is it's just nonsense. Because whether what truth is and what reality is, these are not things that contemporary logicians investigate. They just define systems and they study systems. These questions are questions they're found in philosophy, and they're found in Islamic logic, and they're found in Islamic theology, because you need to know them in order to do theology, and they're correct answers to those questions. And if you study Islamic logic and Islamic theology properly with somebody who's trained, he can teach you the correct answers, and you'll actually have clarity, and you'll be able to see why the central questions of our religion are true, and you won't end up confused as anybody who does contemporary philosophy generally ends up. Which is why I wouldn't encourage anybody after this course to go and study contemporary philosophy. That's actually going to be the topic of the final lesson, which is where do we go from here. So this brings us to the end of this lesson. وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم والله سبحانه وتعالى أعلم وهو حسبنا ونعم الوكيل.